Now we can pretty easily imagine what's going to happen if we throw an acid into the water, even if it's diprotic. We can think in sulfuric acid, we're going to have our first proton pop off. Once all those first protons have popped off, the second protons are going to begin popping off if pH permits, and if the equilibrium constant allows. Now let's go for the opposite case for a second. Suppose we have the sulfate ion. We throw sulfate ion into water, A2-, it's going to start grabbing some protons from the water, and it's going to begin associating into probably HSO4-. Now, it might be able to grab a second proton, but that's going to be a real reach. We're going to have a small concentration of that intermediate form in the first place, and its equilibrium constant is probably pretty small. So, if we just throw in, I'll use my oxalic acid case from before, if I throw H2OX into water, probably the only equilibrium I have to worry about is one of these protons popping off, and very, very crudely, I'm not going to write a complete balanced equation, it creating HOX-. If I did the opposite and I did OX2- and chucked that into some water, it's probably going to grab an H plus onto the OX and become the single minus as well. Alright, so we probably don't have to worry about one or the other as long as we're starting from one of the ends. But what if we were to take the intermediate form instead? What if we took the structure that I have drawn here, HOX-, which means it was probably sitting there on the shelf with an associated salt, maybe NaHOX. What if we throw that into some water? Now let's do that more generically. Now, we can assume that this is going to be a strong electrolyte, so that's going to pop right off, give me HA-. When I have the HA- that I've just thrown into the water, it's going to start giving up protons and becoming A-. It's going to start grabbing new protons from the solution around it and grabbing H2A. And also notice that once it kicks off some protons, other HA- can then grab those protons and associate. So what we might expect is to have all three of these species at the same time. The question becomes, how much of it are we going to have? And that's going to be a pretty complicated problem. So complicated, in fact, that I've just verbally mentioned three different reactions that we're going to have. We're going to have this reaction here. We're going to have this reaction here. And then, even though it's already written, I'll call it a different reaction for the moment. We're going to have this H plus now associating with HA- present in solution. So a piece from here and a piece from here going back to form that one. So you can see this is going to be a pretty complicated system of equations. We're also going to have the autoionization of water and anything else happening in our solution. So we would have to use systematic treatment of equilibrium and really crank through this. Rather than do that, we're going to jump straight to the end game. The book has already done that, and they've come up with an algebraic solution, and this is going to be an exact solution to this whole system of equations. Concentration of H plus will equal the square root of our two equilibrium constants times HA minus. Now let me point that out. We've got our starting concentration, we've got our two equilibrium constants, in other words, how much of it's going that way and how much of it's going that way. And it makes a lot of sense, probably, for us to have both of those pieces there. Now, we're also going to have the term about HA1 over here, and how Kw is going to interact with all that, because that's giving us some more H plus and kicking things back together. And then we're going to have this down in our denominator, and I'll spare you the entire derivation and conceptual derivation. But all the pieces there kind of make sense as being involved in the equilibrium of our intermediate form. The thing is, that's going to be a pretty nasty one to solve still, because we're going to have to do a lot of very careful work to control our system down to the point where we only have that number of unknowns, or we're going to have to bring in lots of additional information, lots of cross-canceling, lots of cross-solving. Or we can do the other thing that you frequently see in the book. We can make observations. I'm not going to say assumptions. We can make observations. Now we know that Ka1 and Ka2 are going to be pretty small compared to other numbers that are in most equations. I mean, these are typically going to be on the order of times 10 to the negative something, right? We saw in a couple of, in the last video that we had, I think, times 10 to the negative 2 here and times 10 to the negative 5 for its exponents. So these are reasonably small. Now, we can say from that that little of our HA is going to be reacting away. So suppose that, and I left out the minus sign there just for a little bit of simplicity. So our intermediate form, not a whole lot of it's reacting away into our two directions. So from that we can probably assume that we stay very close to our formal concentration for this, because they're just not going to be eating up a lot. Now when we plug all that in with this assumption, we end up getting this equation instead. We have our Ka, Ka. Our formal concentration was probably a given in our problem. Ka, that's a table value. Kw, we have that memorized. Another table value from before, and the same thing we started our problem with. So you can see with very little information, we can get a pretty good estimate of our pH for an intermediate form if we just throw that into solution. Now there's also a crude ballpark, and I really want you to think of it as a crude ballpark. If you just need to have some benchmark idea to check your work, or to have some feeling for what is likely to happen when you throw this in solution, you can say that your pH will probably be right around, and in fact let's make sure we emphasize right around, the average of your two pKa's. Now, I frequently see people try using this one all of the time. That's a terrible approach. This is a crude ballpark. This is a form that has a lot of assumptions in it, but is good enough for almost all the work we're going to do. In a perfect world, we're going to go with the systematic treatment of equilibrium and use the iterative solution until we get a pretty well-refined value. We don't live in a perfect world. We're usually going to use this form. This is supposed to be a crude ballpark. So please don't seize on that one and ignore the real equations that we should be using. This is what happens when you throw our intermediate form into water.